Good morning. Happy Thursday. Hope everybody's doing all right this morning. We are going to finish section 4.3. There's only one more example to do there, so we'll finish that up. We'll get into 4.4 today. I was actually looking ahead to see how much more we've got in chapter 4. It actually looks like we might be able to get this test in before the break, which was actually my goal to begin with, and so I think that's my plan right now. What that means, though, is I will post the test on Sunday night at midnight. And I won't make it due until Wednesday. And I know Wednesday is not an actual class day, but you've got Monday and Tuesday to do it if you want to do it before the actual break. But I'm going to give you that one extra day also if you want to use that break day to actually do your test. Okay, so you'll have 3 days to actually go in and take the test this time. Again, if you want to do it Monday or Tuesday, that's perfectly fine. If you want to wait until Wednesday, because we'll probably do the review on Tuesday. So that way you've got that extra day if you want it. Okay, so that's the plan right now. Test posted Sunday night, due Wednesday night of next week by midnight. The homework on sections 4.1 to 4.3 is still due by midnight tomorrow night. Okay, so just make sure you get that done. And then I'm probably going to push the 4.4 and 4.5 homework to Tuesday of next week. I think I've got it on Monday right now. So that those last 2 sections, those will be due Tuesday of next week. Okay, but that way I can get this test in before the break. I can get all those graded, and then that way, if you're trying to make a decision about whether to drop the class or not, you'll have an updated grade with 4 of your 5 test grades already in there, and then you can make that decision because you have to drop if you're planning to drop by the Tuesday after the break. Okay, so that's the last day to drop without receiving a WF. All right, any questions, comments, concerns right now about anything that I just said? All right. So, like I said, this is still 4.3. We got this last example here, and then we'll move into 4.4 today. So, in this one, we're just trying to find the error. So, it just says, what's wrong with this calculation? Okay, so I want you to look through this. And if you see something that looks incorrect, let me know. All right. So, does anybody see any steps here that look incorrect? Okay, so let's do this. Let's actually work through the problem, right? And let's see what you would do on each step. So if you saw this original problem right here, what would you do? So we're looking for the integral from -1 to 3 of 1 over x squared dx. What would you do with that? Okay, so in general, right, when we see an integral, we can find the antiderivative. Okay, so how would you find the antiderivative of that? So if you got 1 over x squared and you wanted to find the antiderivative, what would you do? Okay, good. Rewrite it as x to the negative 2 first, right? So I'm going to change this to integral from -1 to 3 of x to the negative 2 dx. All right, so now if we find the antiderivative of x to the negative 2, how would you find that antiderivative, or what would it be? So if you've got x to some power and you're looking for an antiderivative, what's our process for doing that? Okay, good. We add 1 to the exponent, so -2 plus 1, that's actually going to give us -1. But then we also have to do what? Okay, good. There has to be a negative out front because remember, it's always 1 over whatever that new exponent is. So 1 over -1. And our limits of integration here are from -1 to 3. So that second step there actually looks right, Because we've got the x to the -1, we've got it over -1, so that piece checks out. All right, now once we have that antiderivative, what would we do next? Good. Now we can plug in our values. Remember, we start with the b value, which is our upper limit, and then we go to our lower limit. So this is going to be 1 over -1 is just -1 times 3 to the -1 minus -1 times -1 to the -1. Right, so if we simplify that now, what's -1 times 3 to the -1 power? What would that look like? What would 3 to the negative there, right? So 3 to the -1 just becomes 1/3, and we're multiplying by a -1. So it just becomes a -1/3. And then down here, we've got this minus a -1 times -1 to the -1 power. So -1 to the -1 power is 1 over -1. Multiply that by -1, that becomes a +1, but then we're subtracting it, so that becomes -1. Okay. So those 3 negatives there just become a negative. And now if we do -1/3 minus 1, what does that give us? -4/3, right? So based off of all of that, it looks like there's no mistake here, right? So the question is, what's wrong with this calculation? Look back at the original integral. What has to be true about your function in order to calculate an integral like this? This is based off part 2 of the fundamental theorems. Let me go back to that. So what's the first thing that this says? It has to be continuous, right? So if we look at our function now on this interval from -1 to 3, is 1 over x squared continuous on that interval? No. Where would there actually be a discontinuity for 1 over x squared? Where would that function be undefined? At 0, right? Because we can't have 0 in the denominator. So if you put 0 in for x, that would give us 1 over 0 squared, which is undefined. So because this thing right here is undefined at x equals 0, it's not continuous there. And in this case, 0 is in the interval from -1 to 3. We can't do this calculation at all. Okay, so be very careful, because it's really easy just to get caught up and say, oh yeah, like I'm going to take it and make it x to the -2, find my antiderivative, plug in my values, but only do that if you're allowed to even do that to begin with. Okay, so this one right here is not continuous on that interval, therefore you can't do this calculation at all. Okay, any questions on that? If you think about it, what happens is we've got an asymptote at 0. Both of those are actually going up towards positive infinity this time because of the x squared. And so you have this infinite amount of area because these points never come together. So you can't actually calculate the area under that curve because there's no set area under that curve now. Okay. All right. So that's that one. So like I said, now we're going to move on to section 4.4. All right. So everything we've done so far has been what we call a definite integral, right? We've had upper and lower limits of integration. We're able to find a specific area under that curve. Now we're going to look at what's called an indefinite integral, where we don't have those limits of integration, and so our answers are actually just going to be functions instead of numerical answers. Okay. All right. So indefinite integrals, the integral of f of x dx equals big F of x, the antiderivative, just means that the derivative of the antiderivative is equal to the original function, right? Okay, so we're still doing basically the same process. We just don't have numbers to plug in anymore. So we're not going to get numbers for answers. We're going to get functions for answers. Now, all of our same properties still apply here. So if you have a coefficient in front of your function, we're allowed to pull that outside of the integral. If you have a constant, the antiderivative of a constant is just the constant times x. Okay, so we get kx here. Notice, though, when we do this, just like with our original antiderivatives back in chapter 3, we have to have that arbitrary constant. Okay, so make sure you have the plus c whenever you're finding these antiderivatives if there are no limits of integration. All right, then our integral of sine of x dx is just negative cosine x plus c, again because sine x, the antiderivative, gives us negative cosine. Secant squared x, its antiderivative is tangent x, so that integral is equal to tangent x plus c. Same thing with secant x tangent x dx, antiderivative there gives us secant x plus c. We're allowed to split up addition just like we did with our definite integrals. Okay, so if you see that, you're allowed to split it into two separate integrals. Power rule, we're just raising the exponent by 1, dividing by the new exponent, or multiplying by 1 over the new exponent, however you want to think of that. And then we have our other trig functions down here, they're antiderivatives. Okay, so whenever you're calculating an indefinite integral, this is going to be almost identical to what we did back in 3.9 at the end of chapter 3 by just finding antiderivatives now, okay, because we don't have any numbers to plug in. Any questions there? All right. So let's find the general indefinite integral here for 10x to the fourth minus 2 secant squared x dx. All right, so what would you want to do first with this integral to be able to find the value of the integral? Okay, so we need to find the antiderivative, right? And it's up to you whether you want to just go straight through and find the antiderivative as is. You could also apply some of your properties of integrals and split this thing up and pull things out, right? If that helps you, that's fine. Okay, but we could just go straight through and find it here. So if we're just looking at 10x to the fourth, how would you find the antiderivative for 10x to the fourth? Okay, good, right? So we have our 10 on the outside. We're going to multiply that by, raise the exponent by 1, so that's x to the fifth. And then we have to multiply by 1 over that new exponent. Okay, so there's our antiderivative for that. Then we have our minus. What would the antiderivative of 2 secant squared x give us? Good, 2 tangent x. So we keep the 2. Antiderivative of secant squared is just tangent. And then with any of these general antiderivatives or indefinite integrals, good. We have to have the plus c at the end here. Okay, so now we'll just clean that up. 10 times 1/5 is just going to give us 2. So 2x to the fifth minus 2 tangent x plus c. Any questions on that one? Now, the nice part here is we can just take the derivative of this answer and make sure it gives us what we started with, right? So if you ever want to check the derivative here using power rule, 5 times 2 would give us 10x. Drop the exponent by 1, that's a 4. Minus 2, derivative of tangent is secant squared x. Derivative of a constant is 0. This is the function we started with on the inside, so we know that this is our answer now. So if you ever want to check, just go back and take the derivative of what you get, make sure that's the function you started with inside the integral now. All right, let's take a look at this one now. So we've got cosine theta over sine squared theta d theta, and we're trying to evaluate that integral. Now, we don't know how to do anything involving fractions, right? If we've got a quotient inside of an integral, we don't know how to do that. So what might we want to do first here to help us evaluate this integral? Okay, so when you say bring it up, what do you mean by that? Okay, so if we bring up the denominator, I'm just going to write what that would be, and we'll see if that helps any. So we got cosine theta times sine to the negative 2 theta d theta, right? So if we bring it up, we have to make that a negative exponent. So that's what we end up with. Well, now I've got a product, right? So I've got cosine theta times sine to negative 2 theta d theta. Do we know how to find that antiderivative? We don't, right? Okay, so if there's a product there, we're not going to be able to do anything with that either. So we need another way to think about this one, another way to rewrite it that might help us to actually evaluate it. So any other thoughts on what we might be able to do here? So I'll give you a hint. Think about your trig identities and how we might be able to rewrite this thing. All right, so we could try writing sine squared as 1 minus cosine squared. So let me just write that out, and we'll look at what happens if we do that, because that is true. Now, if we do that, though, we still have a quotient. I can't split this up, right, because I have subtraction in the denominator. So there's really no other way to simplify that at that point, right? And again, we don't know how to calculate the antiderivative for a quotient like that. So even that substitution is not really going to help us here. Think about it this way. What does sine squared theta mean? So in general, what does it mean to square something? Sine times sine, right? Okay, so I'm going to change this to cosine theta over sine theta times sine theta d theta. Now, at that point, I can split this into two separate fractions, and I'm going to call one of those cosine theta over sine theta. What would the other fraction have to be then? 1 over sine theta, right? So 1 over sine theta d theta. Now, if we look at each one of these, is there a way we could rewrite this now? Okay, so not secant, right? Let's look at the first fraction. Cosine over sine is what? So if you do cosine over sine, that's the same thing as what trig function? Cotangent, good, right? So remember, sine over cosine is tangent, so cosine over sine, the reciprocal, should be cotangent theta. What about 1 over sine now? That one's cosecant, good. So we end up with cotangent theta, cosecant theta, d theta. Do we have an antiderivative for cotangent theta, cosecant theta? It's going to be negative cosecant, right? Okay, so in this case, we just get negative cosecant theta. And like you said, we need the plus c. So this would be our answer this time. All right, so there will be cases, again, whenever you see a fraction like that with trig in it, for the most part, right? And we're going to look at some in the next section where we can actually rewrite this in other ways and think of it that way. But for a lot of these, if you can use your trig identities, rewrite it, a lot of times you're going to get a form that we can actually take the antiderivative of. Okay, so think about how you can split it up, rewrite it using your trig identities, and then take the antiderivative if you have something that you can actually take the antiderivative of. Any questions on that one now? All right. Let's take a look at this one. So this time we have a definite integral, right? So this time we're going from 0 to 3. We have x cubed minus 6x dx. Okay, so what would you do first? Good. Find the antiderivative. So if we go term by term here, x cubed, what would that antiderivative give us? Good. 1/4 x to the fourth, because we raise the exponent by 1, multiply by 1 over the new exponent, minus, and then what about 6x? Good. Right, so it's going to be 6 times x squared times 1/2. And this time we've got 0 to 3, so we don't need the plus c this time. And like you said, this is just going to give us 1/4 x to the fourth minus 3x squared from 0 to 3. All right, now what can we do? Now we can plug in our values. Remember, start with your upper limit, so that's the 3. So we have 1/4 times 3 to the fourth minus 3 times 3 squared. That's just the first part, right? Minus, now we're going to plug in the 0, so 1/4 times 0 to the fourth minus 3 times 0 squared. All right, so if we simplify what we have in these first brackets here, what's 1/4 3 to the fourth minus 3 times 3 squared going to give us? Good, right? So this is negative 27 over 4 minus, what do we get in the second set of brackets? That's just 0, right? Okay, because 0 to the fourth is 0 times 1/4, still 0. Same thing with the 0 squared times 3. So all that's 0. So overall now, this is just going to give us negative 27 over 4. Or again, if you prefer, I think this is negative 6.75. Is that right? Yep. So either one of those answers there. Now, these numbers might look familiar because back in section 4.2, we actually did this problem using our limit definition. And remember, that's the one that took up like 2 full slides to actually work through all that. In this case, though, in just 3 or 4 lines, we're able to actually find the value of this. Okay, so again, the shortcuts are very, very helpful, and that's why I said, the homework now, if you want to go back and do like the 4.1 and 4.2 stuff using shortcuts, that's fine. Make sure you still know how to do the limit definition, okay? But I don't want you to have to do that on every single problem for sure. Any questions on this one now? Possibly. Okay, so the question is, the one where we have to divide it up into rectangles, will that be on there? It's either going to be an infinite number of rectangles or it's going to be a set number of rectangles, right? I haven't decided yet. I need to actually sit down and make the test and think about how long each one's going to take. But it'll be one of those 2 types. Either I say, all right, here's your region. I want you to approximate the area using 6 rectangles, something like that. Or I would say, I want you to find the exact area using the limit definition to actually calculate the exact area. Okay, so it'll be one of those 2 types, but I haven't made the test yet, so I don't know exactly which one it's going to be. Okay. No, there is no shortcut for the approximation. Okay, so the approximation, you still have to go through and figure out what are the x values, plug those in to find your heights, add those together, multiply by the width. Okay, so that one, there is no shortcut for that. Any other questions? All right. So again, we want to evaluate this integral. This time, again, we have a definite integral because we have 0 and 12 as our lower and upper limits. So what would we do first here? Okay, good. Find your antiderivative. So if we go term by term again, x is going to give us what? Perfect. 1/2 x squared minus, and then 12 sine x should give us what? Good. So we're going to have our 12 times negative cosine x. And we're evaluating this from 0 to 12. Okay, so now if you want to, right, the two negatives here are going to make a positive. So this is just 1/2 x squared plus 12 cosine x. All right, now what do we do? Now we can plug in our values. Good. So we have 1/2 times 12 squared plus 12 cosine of 12 minus 1/2 times 0 squared plus 12 times the cosine of 0. All right, so cosine of 12 is not going to be nice, right? So I would leave that. That's an exact value. What are we going to get for the 1/2 times 12 squared, though? Good, right? So this is 72 plus 12 cosine of 12 minus, now if we do this piece over here, what's that going to give us? Okay, cosine of 0 is 1, but what do we have to do with that? Multiply it by 12, right? So that's actually going to give us 12 now, so we're subtracting 12. And now if we combine like terms, what are we going to get? $60. Good. 72 minus 12 is 60 plus 12 cosine of 12. That's an exact value. That would be my answer now. And so be very careful again, especially with the trig ones. Don't just assume when you plug in zeros you're going to get 0. In this case, cosine of 0 is 1. 12 times 1 is 12. So we're actually subtracting 12 in that second set of brackets now. The other thing that's a common mistake that I see all the time is when you have multiple x's here, people want to plug in the 12 for the first x and the 0 for the second x. So just take your time. Remember, we're plugging in 12 for both, then we're plugging in 0 for both, and then we're subtracting whatever that result is. Okay? Any questions on that one now? All right. So now we want to evaluate this integral. Again, a definite integral from 1 to 9. 2t squared plus t squared over the, or times the square root of t minus 1 over t squared. And this should be dt, sorry. All right, so what do you think we're going to want to do first here? Okay, we can bring up the t squared. So now I'm going to have the integral from 1 to 9. It's going to give us t to the negative 2 times 2t squared plus t squared square root of t minus 1 dt. All right, then you said distribute. So if we distribute here, what's t to the negative 2 times 2t squared? Two, right? Because the t to the negative 2 and the t squared, that becomes t to the 0, which is just 1. So that's 2 times 1, which is 2. What if we multiply t to the negative 2 times t squared square root of t? So let me write out what you just said there. T squared times t to the 1/2. If you actually multiply those, remember you would add the exponents. So this would be like 4/2 plus 1/2. This would be t to the 5/2 if you actually multiplied that. Okay. Well, in this case, think about it this way. I've got a t to the negative 2, and I'm multiplying by a t to the positive 2. Those are actually going to cancel, and what's going to be left over? Just the t to the 1/2, right? Just the square root of t. And if you want to go ahead and write it as t to the 1/2, that'd be great, because we're going to have to take the antiderivative eventually. All right, and then that last term, t to the negative 2 times the negative 1, is going to give us what? Good, just t to the negative 2. All right, so any questions about how we got that step right there after we distributed the t to the negative 2? Now, another way you could have done it is just divide each of your terms by t squared, right? Because 2t squared over t squared, that's going to give us 2. Then if you add t squared square root of t over t squared, that's going to be the square root of t. And then negative 1 over t squared is just going to be negative t to the negative 2. Okay? But either way, it works, right? If you make it a negative exponent and distribute it, it's the same thing as just dividing each term by that. So whichever way you see it first is fine. Just be real careful when you're distributing. Okay, just remember you're adding exponents at that point if you do it that way. Okay, now once we've got that line, now we can do what? Okay, we can't plug in yet because we still got to do what? We have to take the antiderivative first, right? Because we haven't gotten this out of the integral yet. Well, if we go again term by term here, what's the antiderivative for 2 going to give us? 2t, good, plus antiderivative of t to the 1/2. Good. 2/3 t to the 3/2, because again, we're adding 1 to the exponent, that gives us the 3/2, and when we divide by 3/2, that's the same as multiplying by its reciprocal. That's where the 2/3 comes from. All right, and then we have our minus antiderivative of t to the negative 2. Good. So we have a negative t to the negative 1. And we're evaluating all of this from 1 to 9. And now it's kind of up to you how you want to simplify this. I'm going to write this as 2t plus 2/3 t to the 3/2. This is going to become a plus, and then t to the negative 1 is 1 over t. All right, so now we can actually just go through and substitute, right, at this point, because we've taken our antiderivative. Start with the 9. Again, the 9 is going to go in for all of those t's here. So we're going to have 2 times 9 plus 2/3 times 9 to the 3/2 plus 1 over 9. Now we substitute in our lower limit. So we have 2 times 1 plus 2/3 times 1 to the 3/2 plus 1 over 1. Right, now, at that point, you can just put all that right into the calculator, or if you want to go term by term, you can do that also. Okay, so try that, see what you get, and if there's any discrepancies, and I'll go back and go term by term to make sure everybody's clear on how we get the answer. Perfect. 292 over 9 is correct. Okay. Or this would be 32.4 repeating, right, if you wanted the decimal. In this case, because it's a repeating decimal, you probably want to use the fraction there. Any questions about how we got that answer? So I'm happy to go through and simplify it term by term if we need to. All right. So yeah, just be careful there. Like I said, once you get it to that line, if you want to put all that in the calculator, even on the test, that's perfectly fine. Just be very careful with your grouping symbols and things to make sure that you've got everything in there correctly. Otherwise, I would say go term by term just to double check and make sure. Okay. All right, now net change theorem. So the integral of a rate of change is the net change. So basically we're saying, the derivative of big f of x is the same thing as f of x, right? And we're taking the integral from a to b now. That's going to give us big f of b minus big f of a. We're just calculating the antiderivatives, plugging in the values. But this thing down here now is called the net change, right? So we're basically finding what is the net change in the values of our functions from a to b. That's all. All right, so where this comes in is with our particle motion, right? So when you have position, velocity, acceleration, things like that, we can use this now to find the net change in position of whatever object we're looking at. So we got a particle moving along a line. The velocity here is going to be t squared minus t minus 6, measured in meters per second. We want to find the displacement of that particle on the time interval from 1 to 4 seconds. In other words, we want to know what's the net change in its position over that time period. Well, if I'm given velocity here and I want to know the displacement, the net change in position, what would I want to do? Okay, we need to know something about position, which is S of t. How would you find S of t given what we have? We need an antiderivative, right? Because that's how we go from velocity to position. Well, in this case, another way to find an antiderivative is to integrate, right? To find the integral. So I'm going to set up an integral here. But in this case, I know an upper and lower limit for my integral. So what are the upper and lower limits going to be here? 1 and 4, right? So this is going from 1 second to 4 seconds. So we're going to go 1 to 4. We're going to take the integral of our velocity function, t squared minus t minus 6 dt, just to tell us that t is the independent variable. And so now if we find the antiderivative, that's position, then we're going to plug in the times and we're going to subtract to figure out the net change in that position, which is displacement. Okay, so whenever you're given velocity, you're asked for displacement, this is going to be your setup. Find your antiderivative, plug in your upper and lower limits, subtract them, that gives you displacement. What's the antiderivative going to be here? Good, so 1/3 t to the third minus 1/2 t squared minus 6t. That's it. We have values this time to plug in, so no plus c, just 1 to 4. All right, so now what are we going to do? Plug them in. Perfect. Start with your 4. So we have 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4. Then we're going to subtract 1/3, 1 to the third, minus 1/2, 1 squared, minus 6 times 1. And again, at that point, you can just go straight to your calculator. Just be very careful with your grouping symbols when you do this and see what you get. Good. -9/2 or -4.5 if you prefer the decimal. Now, on this problem, we are going to have units. Okay, so think about what units this is going to represent now. These are meters. Good. So displacement here is the distance that's been traveled, right? Okay, so from starting to ending position, -9/2 or -4.5 meters is our total displacement. Now, what that tells us in this case, if we're moving along a straight line, let's assume horizontal left to right, because it's a negative value, that just means we're farther to the left than where we started by 4.5 meters now. Okay. Any questions on that part? All right, now part B. Now we want to find the distance traveled during this time period. This is different from displacement. Okay, displacement is only the net difference in where we started and where we ended up. Distance traveled, though, accounts for all of the movement. So basically, my particle, if it started right here, maybe it moved this way, and then it moved back this way, and then it moved back this way, and it ended up here, right? Well, the displacement is only going to measure that difference between where it started and where it ended. But the total distance traveled is a lot more than that. Okay, so what we've got to figure out now is how far did this particle actually travel to get from where it started to where it ended. Okay, to do that, we need to think about where it changes direction, because every time it changes direction, we're going to be adding in more distance, right? How could we figure out where this particle changes direction? We don't need concavity necessarily, okay? So we can actually do it just with what we've got here. So think about what you know about when something changes direction. Okay, so what's going to be negative versus positive? Okay, so I agree with that, but in terms of actual functions that we're working with, right? Position, velocity, acceleration, those types of things. Where would we be looking for negatives and positives for changes in direction? All right. Let me do this. Let's just imagine that you're throwing a ball in the air, right? Okay, so if you throw a ball up in the air, its height's going to increase, but eventually it's going to start to fall back down again, right? Where does that ball change direction? Just give me a general idea of where it changes direction. What would you call that? Okay. It's a critical number, right? So it's basically right here at the vertex. That's where the derivative is going to be equal to 0 because we have a horizontal tangent, right? And that's how we find critical numbers. Well, in this case, what function represents the derivative of our position? So if you take the derivative of a position function, what do we get? Velocity, right? So what do we want to do with the velocity function to figure out where it changes direction? Set it equal to 0, right? Because that's going to give us the critical numbers. That's going to tell us where we have those horizontal tangent lines, and that's going to tell us where we change direction now. Okay, so take your velocity function, t squared minus t minus 6, and we're going to set it equal to 0. Because remember, if you're throwing that object, right, it hits a peak, and then it starts to fall back down, and for a split second, it's frozen, right? It's not moving at all. And so that's where the velocity is going to be equal to 0 now. So that's what we're looking for. That's the change in direction. How would we solve this equation now? Okay, good. Factor first. So we're going to get t minus 3, t plus 2. And if we set each of those factors equal to 0 now, that's going to give us t equals 3 and t equals negative 2. Perfect. Now, do we need both of those values? Why not? Okay, we don't need the negative value because it's not in our interval, right? We're only looking from 1 second to 4 seconds. The only one that works there is this one. Okay, so that's the only place we care about where it actually changes direction. It still changes direction at time negative 2 seconds, okay, but that's not in our interval. We don't care about it. So now what I want to do is I actually want to do the same thing we did in part A, But instead of going all the way from 1 to 4, I'm going to split it into two separate integrals where I go from 1 to 3, and then I go from 3 to 4. So we're taking the integral from 1 to 3 of t squared minus t minus 6 dt. And then we're going to take the integral from 3 to 4, t squared minus t minus 6 dt. Now, the only additional thing we have to remember here is that distance is always positive. So what could we do with these values to make sure they come out positive? Absolute value. Okay, so I'm going to take the absolute value now of both of these integrals. Okay, so just in case one or both of them come out negative, okay, and one of them will because there's a change in direction there, okay, we have to make sure we take the absolute value here. Okay, any questions about that setup or how I got any of these values now? And that's the difference in displacement and distance traveled. Displacement is just the straight integral from whatever to whatever. That's going to tell us what the net change is in our position. Distance, though, we have to figure out where it changes direction, split your integral there, and then we have to make sure that everything's positive. Okay? Well, our antiderivative is still going to be the same. That hasn't changed. So this is 1/3 t cubed minus 1/2 t squared minus 6t evaluated from 1 to 3, and we're taking the absolute value of all that, plus 1/3 t cubed minus 1/2 t squared minus 6t, this time evaluated from 3 to 4, and we're taking the absolute value of that. All right, so now we can plug in. I'm going to write this out. If we plug in the 3 first, we've got 1/3 times 3 to the third minus 1/2 times 3 squared minus 6 times 3. Then we're subtracting. Plug in the 1. That's 1/3 1 cubed minus 1/2 times 1 squared minus 6 times 1 plus, and now we have to do this one over here, so we're plugging in the 4 first. So it's 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4. Hopefully I can fit all this in here. Plug in the 3. 1/3 3 cubed minus 1/2 3 squared minus 6 times 3. All right, so hopefully you know exactly what that says, okay, because I know it's kind of small and I squeezed it in over on the side. All right, but evaluate each of those now by plugging in the 3 and the 1, then plugging in the 4 and the 3, subtract those values, take your absolute value, and then we're going to add those two things together. Okay, so do one at a time here. Just do the first one and let me know what you get from 1 to 3 first. Okay, so that one's 22/3, or is that the total? That's just the first one. That's the total. Okay. Let's see. Okay, so that's just the first. Yeah, so 22/3 there. Okay. Plus, all right, and then what do we get for the second piece? Good. 17 over 6 is correct. Okay, and so now if we add those two together, what should we get? Good. 61 over 6. All right, and what are the units going to be here? Okay, so be careful, right? Think about what we just calculated. It's just meters, right? Because again, we're just looking for a distance traveled. So this is still just going to be meters this time. So 61 over 6 meters is the correct answer. And so in this case, the first one's the one that comes out negative. It's actually a negative 22 over 3, but because we're taking the absolute value, that's why it's positive. And then we add that distance to the 17 over 6. That's where we get that. If you had kept it negative 22 over 3 and added the 17 over 6, what will happen is you'll get the same answer we got for part A. Okay, because if you split those integrals and don't take the absolute value, it's just going to give you the displacement. Any questions there now? All right, let's take our break here. So 11:03, 11:08, we'll get started back up, and we'll actually move on to section 4.5. All right. So, like I said, this is 4.5. This is actually the last section in this unit. It'll probably take us into Monday to finish it up, though. So, like I said, we should finish up. Might even get to the review on Monday, but the practice test is posted if you want to start looking at that over the weekend. And the test will be posted Sunday. And again, do it Wednesday, even though Wednesday is not an actual class day. That'll give you 3 full days to do it if you want, or if you want to get it done before the break, you can get it done by Tuesday. Okay. All right, so substitution rule. So the substitution rule here tells us if we have a composition of functions inside of an integral now, we're basically going to do a u substitution, but in reverse. So it's like a chain rule, but in reverse now, to figure out what that antiderivative is going to be. Right? So in other words, we're going to look for the inside function here. We're going to let u be equal to whatever that is. And then we're going to do those substitutions here so that we can actually find the antiderivative of something that's simpler than what we started with. Okay. All right, so let's take a look at this one here. We want to find the integral of x cubed times the cosine of x to the fourth plus 2 dx. All right, so notice here we have a product, right? We haven't done anything with products up to this point. But we also have this composition of functions where we have an x to the fourth plus 2 inside the cosine function. Right? So the first thing we're going to want to do here is to try to rewrite this integral in terms of u. Okay, so what are we going to let u be equal to this time? So what would the inside function be? Good, right? So the x to the fourth plus 2, that's our inside function. So I'm going to let u equal x to the fourth plus 2. Now I'm going to try to rewrite my integral just in terms of u's and du's so that I can actually find the integral here. Well, I know this is going to become cosine of u then. What's left that I still need to replace at that point? So if I change x to the fourth, we got an x cubed, and we also need to replace what? The dx, right? So identify what you're still trying to replace at that point, because that's what we're going to try to get from this u equals x to the fourth plus 2, okay? Now I'm going to take the derivative of my u value. Well, the derivative of u with respect to x is du dx. Okay, so I want you to write it as du dx because that's going to help us to see what we actually need to substitute into our integral now. What would that derivative be equal to? 4x cubed. Perfect. Now, what we're trying to replace is x cubed dx. So I need to try to get x cubed dx in this equation over here so that I know what I can substitute in place of it. Well, how could I get x cubed dx in this equation now? So if I want to get the x cubed and the dx together, what would you do first? Okay, so think of this just as a basic equation where du and dx are variables, right? If I want to get dx to the other side with the x cubed, what would I do with it? Not divide, because right now I'm dividing du by dx. So what would I need to do instead if I want to move the dx to the other side with the x cubed? So what if I had like 2 over x equals 3? What would you do first to solve that equation? You'd multiply by x, right? You'd move that to the other side and you get 2 equals 3x. And then if you needed to get x by itself, you could divide by 3, right? Well, over here now, I need the x cubed and the dx together. So what am I going to have to do to get the x cubed and the dx together? Multiply, right? So to get rid of the division here, I'm just going to multiply both sides by dx. That's going to leave us with du equals 4x cubed dx. So again, just think of it as an operation, right? Du over dx, the inverse operation is multiplication. I'm multiplying to get the dx to the other side now. Now, I don't want 4x cubed dx. I just want x cubed dx. So what would I need to do next? Divide by the 4, right? So I'm going to divide both sides by 4 now. So this is 1/4 du equals x cubed dx. That's what I wanted, was x cubed dx, because that's what I'm trying to replace. So what can I put in my integral now to replace x cubed dx? The 1/4 du. Good. I'm going to put the 1/4 here. I'm going to put the du here. It doesn't matter where you put any of it, right? But it just makes more sense to me to put the 1/4 in front of the cosine, the du at the end. Okay. So again, first step, identify the inside function. Let that be your u value. Take your derivative. Let that be du dx. Then you want to figure out what are you still missing that needs to be replaced. In this case, we're still missing the x cubed dx. So I want to solve that equation for x cubed dx so that then I can get everything in terms of u's and du's. Okay, that's our ultimate goal, is to get it in terms of u and du so I can actually take the antiderivative now. Any questions up to that point? All right, so now if we take our antiderivative, what's that going to give us? So if you find the antiderivative of 1/4 cosine u, what would that antiderivative be? Good. All right, so we get 1/4 Antiderivative of cosine is sine u. And then in this case, because it's a general antiderivative, what else do we have to remember? Plus c, right? So don't forget the constant here because we don't have any values to plug in this time. Now, there's only one additional step at this point. Because our original integral was in terms of x's, we need to get this back in terms of x. So I'm going to take the u value now, I'm going to plug it back in. So this is just 1/4 times the sine of x to the 4th plus 2. And then we have our constant. This is our answer. So again, the whole goal here, whenever you've got these composition of functions, we don't have any way to do this other than a u substitution, just like we did with chain rule, so that we can get everything in terms of u's and du's. Then it should be a much simpler function to work with. We can take the antiderivative, and then we can go back and plug in whatever our u value was. Now, again, you can check your answer here by actually taking the derivative of this thing. If we take the derivative, you'd have 1/4. You'd have cosine of x to the 4th plus 2. Then we have to multiply by the derivative of the inside here, which is just 4x to the 3rd. Derivative of the constant, though, just becomes 0. 1/4 times 4 cancels out and gives us 1. So now we're left with x cubed cosine x to the 4th plus 2. And that's exactly what we started with on the inside. Okay, so this is just a chain rule in reverse now so that we can actually get the function that we started with on the inside. Any questions on that example before we move on to the next one? All right, let's take a look at this one now. So again, we're trying to find the integral square root of 2x plus 1 dx. All right, so what do you think we should do first on this one? All right, so what would you let u be equal to this time? Perfect, right? So we're going to let u equal the inside, which is 2x plus 1. That's our first step. Good. Now, we need to rewrite this in terms of u's and du's. So how would you rewrite what's inside here now? What's one thing we could do? Good. So this just becomes the square root of u. So what are we still missing this time? Just the, well, we need a du, right? But in terms of just substitutions here, what's the only thing that we haven't substituted for? So the 2x plus 1 became a u, but we're still missing what? From the original. The dx, right? So this time, remember last time we had an x cubed and a dx that we needed to replace. This time we just need to replace the dx. Okay, that's all we're trying to replace here. Well, what am I going to do next then to figure out how to replace dx? Good. Take your derivative, du dx over here. So we have du dx. And what's that going to be equal to this time? Just 2. Good. Now, again, all we're trying to replace this time is dx. So what would you do next? Not quite, okay, because 2 is equal to du dx, right? We want to figure out what dx is equal to. So how would you get dx by itself here? Okay, so we've already got du dx, right, is equal to 2. So the question is, if dx is the thing I want to replace, that means I need to solve this equation over here for just dx. How would I solve that equation for dx now? Think about the last example. What could we do with the dx at this point? Multiply, right? So we're going to multiply here to move the dx to the other side. So that's going to give us du equals 2 dx. Well, we don't want 2 dx. We just want dx. So what do I need to do now? Divide by the 2. Good. So I'm going to divide both sides by the 2. It's going to give us 1/2 du equals dx. Now I know what dx is equal to, so what can I do now? Good. I can plug in 1/2 du in place of dx. So I'm going to get a 1/2 du over here now. So again, the process here, identify your inside, let that be the u value, take the derivative of that, figure out what you still need to replace, right? In this case, it's only the dx that needs to be replaced. So now we just need to solve that equation for dx. On the previous example, we had an x cubed and a dx that we needed to replace. So we wanted to get x cubed and dx together in that case. All right. Any questions about that step? Again, ultimate goal here, get everything in terms of u's and du's, because this independent variable has to match the variable that we're taking the antiderivative with respect to. Okay, so you can't have any dx's left in here because our variable now is u. Now, how are we going to find that antiderivative? So the 1/2 is going to stay 1/2. I know that. But how would you find the antiderivative of square root of u? Okay, we can't plug it back in yet, right? Because we need to actually take the antiderivative before we resubstitute the u value back in. So if you just want to find the antiderivative of square root of u, what would you do? Okay, good. That's what it's going to be, right? Because we can rewrite this as u to the what power? The square root of u would be the same thing as u to the what? 1/2, right? Okay, so that would be my first step, is to rewrite it as a fractional exponent. Now we can just use our power rule to actually find the antiderivative. So again, keep the 1/2 that's already there. We're going to raise the exponent by 1, so that becomes 3/2. We're going to divide by 3/2, which is just like multiplying by 2/3. And then in this case, again, because it's not a definite integral, what else do we have to remember here? Plus c. Good. All right. At that point, we can go ahead and plug the u value back in. We can also multiply the 1/3, or sorry, the 1/2 and the 2/3 here. The 2's cancel, so this just gives us 1/3 times u, which is 2x plus 1 to the 3/2 power plus c, and that is our answer now. So again, make sure don't plug the u value back in until after you've taken the antiderivative, because we need to take the antiderivative with respect to u first, because that's the whole purpose of doing these substitutions, is to make it a function where it's easier. Because otherwise, if you plug it back in, you're just going to get back what you started with. Any questions on that one now? All right, let's take a look at this one. All right, so again, we're calculating an integral. We've got x over the square root of 1 minus 4x squared dx. Now, one thing I will tell you, always look to see if there's a way to simplify first, just like that trig one that we did in the previous section, because if you can simplify it and get it in terms of an antiderivative that we're familiar with, that's going to be your best bet. Okay, but if you can't, then we have to look for other ways, and substitutions are going to be the way that we do that. So here we have x over the square root of 1 minus 4x squared. It is a quotient, but there's no way to simplify this fraction up front, right? So we need to do a u substitution. What do you want to let u be equal to this time? Good. Okay, so everything inside the square root in our denominator. So we're going to have u equals 1 minus 4x squared. All right, now again, we need to try to rewrite this whole thing in terms of u's and du's. So the first thing I'm going to do in my fraction now, I know I can replace 1 minus 4x squared with u. So this is just going to become, I'm going to write it as u to the 1/2, since I know that's going to be what square root of u is anyway. Now, what are we still missing that we need to replace? Good. We have the x up top and we have the dx right here. Both of those need to be replaced. So what am I going to do next to figure out how to replace those? Good. Take your derivative. What is the derivative this time? Negative 8x. Perfect. All right. Now what are we going to have to do if we're trying to replace x dx? Good. Multiply by the dx. That's going to give us du equals negative 8x dx. And then we can do what? Divide by the 8. In this case, that's a negative, right? So it's going to be negative 1/8 du is equal to x dx. All right. Now what can we do? So we solve for x dx. So what can we do at that point? Okay, good. Replace x and dx with negative 1/8 du, right? So in my fraction over here now, or in my integral, I'm going to put the negative 1/8 out front. I'm going to put the du here. So what do we actually need in the numerator of that fraction now? A 1, right? So this is 1 over u to the 1/2. But now I've got everything in terms of u's and du's. Now I've got to think about how I can actually find this antiderivative. So what would you do next? Good, right? So go ahead and bring up the u to the 1/2, make it a negative exponent. So then we're going to have negative 1/8 u to the negative 1/2 du. All right, so now if I'm trying to find that antiderivative, again, I can keep the negative 1/8. I know that for sure. What would the antiderivative of u to the negative 1/2 give us? Perfect. All right, so we add 1, that gives us u to the 1/2. When we divide by 1/2, that becomes 2. So we have a 2 out front now. And again, because it's an indefinite integral, what else do we have to remember? Plus c. All right. Now, at that point, all right, we can go ahead and multiply the negative 1/8 times the 2. That should give us negative 1/4. And I can go ahead and resubstitute the u value back in since I've taken my antiderivative now. So that's going to be 1 minus 4x squared to the 1/2 power. And then we have our plus c. And if you want to write that 1/2 power as a square root, right, you can do that also. Okay, or you can just leave it as 1/2 power. I'm fine either way. All right. Any questions on that one? All right. So let's take a look at this one. This is going to be the last one we do today because the one after this takes a little while and I don't want to rush it. So I'll save that one for Monday. Okay, so if we look at this one now, what's the first thing you would do if you want to find the integral of cosine 5x dx? Okay, good. So what's our u value going to be this time? Good. So 5x is the inside, so we'll let u be equal to 5x. So now let's think about how we can start to rewrite this. So what's one thing I can replace now in my integral? Good. So this is going to become cosine of u. And so what are we still missing then? The dx. Good. That's the only thing I've got left to replace. So what would I do next? Good. Find your du dx. In this case, that's just 5. Perfect. Then what? Good. Multiply to get du equals 5 dx. And then we're going to divide by 5 because we're just trying to replace dx. So that's going to give us 1/5 du equals dx. All right. Now what? Good. Dx now we can replace with 1/5 du. So now we have a 1/5. We have a du. And so at that point we can do what? Good. What is our antiderivative going to give us this time? Okay. So be careful here, right? The antiderivative of cosine is what? Just sine, right? Okay, so we have a positive 1/5 times sine of u. And then what else do we have to remember here? Good. Indefinite integral, we need the plus c. And then our final step, as always, take the u value, plug it back in. So we're going to have 1/5 times the sine of 5x plus c. And that's it. Now, the reason that this one, because this one's a lot more basic even than the last two examples we did, right? The reason they put this one here is to show you, you might get to a point, just like with chain rule, where you don't need to write out the u's and du's and all that every single time. If you just recognize here, oh yeah, the antiderivative of cosine is sine, so I'm going to have a sine of 5x in my answer. And then I know I need a 1/5 to cancel out that 5 on the inside because I'm taking the derivative of 5x. Then I'm just going to put a 1/5 outside. So if you start with some of the more basic ones, right, being able to go straight from here to here, that's perfectly fine. Okay. Now, in a lot of cases, you're going to need to write out the u's and du's because there's going to be so much stuff to replace. But a lot of times when it's just the dx that you're trying to replace, you might be able to do it without showing all those steps. Okay. And if you can, I'm fine with that. If you can't, show the steps. Any questions there now? All right, so like I said, we'll stop a little early today because I don't want to get into the next one and not be able to finish it. So we'll save that for Monday. We'll finish up 4.5 and probably have time to review on Monday. That's kind of the goal at this point. Like I told you before, though, the test will be posted midnight Sunday. I'm going to give you until Wednesday this time to get it done. But if you want to knock it out before the break, that's fine. If you want that extra day, that's fine too. Homework on 4.1 to 4.3, though, if you haven't finished it, that will be due Friday at midnight, so make sure you get that done by the end of this week. The next homework is going to be due Tuesday of next week. That's the 4.4 and 4.5 stuff. So if you get a chance to start looking at that over the weekend, that would be good. Rachel, I'm going to try my best to get through the test tomorrow. So it'll probably be tomorrow by the afternoon. I should have all of them graded. Okay. You're welcome. All right. Any other questions before we go today? All right. Have a great afternoon, a great weekend, and I will see you all on Monday.